Okay, then hello from Berlin, and it's really a pleasure for me to give a presentation here at your seminar. And I want to talk about the thermal evolution of the moon. And so why are we interested actually in the thermochemical evolution of the moon after its formation up to the present day? So we are more concentrated, or in my presentation, starting from the Magma Ocean phase, which is illustrated here, up to today. And there are several processes acting on the planet which will influence the thermochemical evolution. That's first, there are external processes like impacts, also tidal dissipation in the interior, which can modify the thermal evolution. And there are internal processes, mainly mantle dynamics, melt generation, and volcanism, but also magnetic field generation in the core of the moon. And I'm concentrated actually in my presentation on this past year, looking at the thermochemical evolution of the moon, starting from the Magma Ocean phase up to today, due to internal processes. So what are actually the constraints that we have for the thermochemical evolution? Or with other words, what kind of observations do we have that needs to be explained by the thermal evolution? That's first that the lunar highland crust is a product of an early magma ocean. That's a strong constraint because it's the only body in our solar system where we know, or where we have a relict of a magma ocean phase. Another important point is that we have constraint on the timing and distribution of the secondary volcanism, or mare volcanism, how it's called on the moon. We have crustal thickness variation, what you nicely can see on that figure here, where we have a thin crust on the near side of the moon and a thicker crust on the far side of the moon. We also have information about the surface composition. Here I've mentioned the radioactive genic heat sources like thorium, but also the titanium content in the mare basalts, which give us constraints on how the planet has evolved. But I'll come back to that later. Other information that we have is crustal magnetization in the crust, which gives us indication on the magnetic field, on the timing of it. We also have tectonic features showing us global expansion or contraction. I don't address these 2 points here because just, I don't have enough time to really talk about these issues as well. So let's first start about the secondary volcanism or mare volcanism. So the mare basalt covers approximately 18% of the surface, including the cryptomare. And this is only 1% of the entire crust. So it's not a large amount, but anyway, it gives us strong constraints. We have a peak around 3.9 to 3.4 billion years ago, but the volcanism was active actually up to 1 billion years. So what you see here on the figure on the right, the upper one, is the function of the age, the location of the volcanic regions. And as you can see, they are concentrated here on the near side, and on the far side, we only have a few spots. It seems that the volcanism is controlled by the crustal thickness. That means where we have a thin crust, what you can see here, the maps of the crustal thickness. So that when you have a thin crust, volcanic activity is easier than on the far side, or where you have a thick crust. There's one exception, that the South Pole Aitken basin, which has a thin crust, but even there you don't, but you don't see a strong volcanic activity. So the control of the crustal thickness seems to be there, but that can't be the end of the picture. On this slide, we see the distribution of titanium oxide, which gives us constraint about the composition of the basalts. What's interesting is from the Apollo samples, it was originally suggested that the titanium-rich basalts tend to be older than the titanium-poor basalts. But now with new orbital data, the situation is different. We have a wide variation of the abundance as a function of time. What you see here, that's time, and that is the amount of titanium oxide. So we have actually a stronger variation of the old Mare, and for the younger, the variation is a little bit smaller, but there is no trend in this way that you have titanium-rich basalts that are old and titanium poor that are younger. So this we can't see. But this again gives us constraints on the volcanic evolution and the thermal evolution of the moon. On this slide, we see the so-called Pikati region, which gives us the content of thorium on the surface. And this is mainly concentrated in this region, the so-called Procellarum creep terrain, Pikati. And we also have a smaller anomaly in this SPA region, the South Polar Aitken. This is basically the same region where we have also the volcanic activity, as you can see here. But nevertheless, what's interesting and also is important for the discussion how the Pikati is built, that the thorium enrichment is mainly in the non-Mare crust, which you can't really see when comparing that. You have to go much more in detail. But obviously, it's not the volcanism itself that brings the radioactive elements into the crust. And one thing to mention here, the origin of the Pikati is highly debated, and there is no general consensus at the moment. But I come back to that point also later. So what I'm going to present now in this presentation is, I first want to talk about the Magma Ocean, which basically sets the initial stage of the planetary evolution. I will talk about the Magma Ocean solidification, the timeline of that, the fate of the ilmenite-bearing cumulates. That is related actually to the titanium. I haven't mentioned that, but it's important. But depending where the ilmenite is in the mantle, that will influence also the volcanism. I will talk about the Pikati region, whether it can be caused, which has been suggested, by low degree downwelling or low degree upwelling. I will also address how the Pikati region can influence the mantle dynamics. And at the end, I will say a little bit about the secondary volcanism, the duration, and how it is influenced by the crust itself. Okay, let's first start about the magma ocean crystallization. So we know that, as I mentioned, we have a crust on the moon, which indicates there was a magma ocean at the surface. So what you can see here is the radius and the temperature, starting from a totally molten surface. You see here that is the adiabat, which is steeper than the melting temperature. So what's happening if the planet is cooling, that you start freezing from the bottom up. Yeah, and that is just because the adiabat is steeper than the melting temperature. And usually because we have a liquid material and it is vigorously convecting and efficiently cooling, that the whole process is very fast. It can be in 1,000 to 100,000 years. What's happening also, which is important, is that we have a fractional crystallization. So the first minerals that form are heavy and sink down, and so that you, as I said, have a crystallization from the bottom up. Now the interesting or the special case for the moon is now that after 70 to 85 volume percent of solidification, andesite starts to crystallize, and which is then rising and forms the crust. And this is important because it influences also the cooling behavior of the magma ocean. But okay, and then when we have solidification of 95 volume percent, then this, what I've mentioned already, this titanium-rich material, these so-called IBC forms, which is then at the base of the crust at the end. And this is very dense. And the thickness of this layer is approximately between 20 and 40 kilometers. And at the end, we have a strongly enriched radioactive heat source. It's called creep. And that is also something we can typically see on the moon, that we creep-like material, which is strongly enriched in heat sources. So I've mentioned already that the titanium-rich material has a very high density that comes from the enrichment of melt with time when the material is crystallizing, that you enrich iron and also titanium into the last melt. So that at the end, when you crystallize, what you see here is a radius, a function of the density. This is a density profile when the magma ocean is crystallizing and nothing else happens. Yeah? So at the end, and at the top you have this low density crust, and below the crust you have this highly dense so-called IBC layer. And here are different profiles depending on how much interstitial melt is there. I don't want to go into detail there, but the important thing is that is a dense layer on top of a less dense mantle, which is an unstable situation. Yeah, you can imagine. So this tends to sink down. And what you see here, these lines here illustrate the density profile after the so-called overturn. And then at the end, you have a deposition of this IBC layer at the core metal boundary, which then has a larger extent simply because we are looking at a sphere, and you to fill the same material here at the bottom, you need more space in radius. Okay. Before I talk more about this IBC layer, I want to talk about the duration of the magma ocean. So I've mentioned already the first steps before you start crystallizing the crust, that is extremely rapidly. But then you start forming the crust, then creep, and then everything is totally solidified. And the question is, how long does it actually take? That can make a large difference to what is happening in the cumulate mantle below and the mixing of all the material. So here I show you one slide from a model we recently published actually. And what you see here is a model where we coupled geodynamical and the petrological model. So here is the cumulate mantle, which forms rapidly, as I said, until the anorthositic crust is formed, and sandwiched between is a magma ocean. So what we modeled is then the dynamics of the mantle and the cooling behavior of that magma ocean. And on top, as I said, is the crust which forms then this time. That's what you actually see here. This is the depth as a function of time. So this is when the moon formed, and very rapidly you start forming the crust, which is indicated here by the red line or by the dashed or the dotted line. So we are comparing here different cases. One is this with the dotted line here is with a crust where people assume, or where we have assumed that it has the same thermal conductivity than the mantle. And what you see is that the duration of the magma ocean phase ends after 50 million years, and then it stops. But what you need to consider actually is that the crust has a lower thermal conductivity than the mantle, and that is the dashed line here. And in that case, we use the conductivity of 2 Mad per meter in Kelvin, which is a realistic value for the anorthosite. And then you see that the duration of the magma ocean is prolonged by a factor of 3. So we end up about 150 million years. And on top of that, you can imagine when the duration is already long, during that time, the mantle starts to convect. And when it convects, because the temperature is already very high, it's easily to generate melt due to that convecting process, yeah, because we bring material up where it starts to melt. And this volcanic heat transport brings heat into the magma ocean and further prolongs the magma ocean solidification. And for this specific model, it ended to after 200 million years. So this is kind of what we see with the more detailed model here, that we have lunar magma ocean solidification, which takes around 150 to 200 million years. Previous models have actually suggested 10 to 30 million years, but what they neglected is simply the lower thermal conductivity of the crust, and also the influence of the volcanic heat transport or magmatic heat transport from the convecting cumulative mantle into the magma ocean. So I think that is a kind of robust result that the magma ocean solidification takes about that long. Okay. Another issue here about the magma ocean, I've mentioned already this titanium-rich basalts or the variation of that, and it is assumed that it comes actually from this so-called IBC layer because it is enriched in titanium. The question is, what is actually the fate of this IBC layer? We've seen that it is dense and sits on top of the cumulative mantle, which has a lower density, so it tends to sink down. And that is something people have studied a lot. And the question is actually, will it sink at the core mantle boundary layer? Simply there, will it be mixed in the mantle, or possibly it remains below the crust? And the other question is, what is the degree of the downwelling? It has been suggested that the Pikati region, this where we have a strong anomaly in the radioactive heat sources, can be explained actually by 1 degree downwelling. Yeah. So is it possible that this layer sinks as a 1 degree process into the interior, and could explain the Pikati region? So let me first address the first point here. How is the mixing of this ilmenite layer? So here I show you a model where we studied that, assuming that the magma ocean crystallized, including the IBC layer, and nothing happened before. So what you see here is the IBC layer. That is a density profile with a radius as a function of the radius. That is the assumed temperature profile, which consists of the crystallization temperature of the magma ocean at the end of the magma ocean. And this is the assumption about how the heat sources are distributed. Okay, these are details now. But let me show you before I talk about how the process works of this mixing and sinking of the IBC layer, I want to show you one important parameter, that's the mantle viscosity, which can be described by an Arrhenius law, which is given here. And important parameters is the activation energy and the activation volume. Here are the values listed. So what we see here is the function of depth and temperature, a typical temperature profile in the interior of a planet. So when we take a look how the viscosity looks like, you see that when we at the surface where we have a low temperature, we have an extreme high viscosity, and it is then decreasing because of the increase of the temperature, and then in the interior it's increasing a little bit with depth and because of the pressure dependent. But this is not the important thing. The important thing is that on the top, because we have a very extreme high viscosity, the surface is stagnant. Yeah, so the convection basically takes place underneath that stagnant lid. And the thing is now, depending where the IBC is located, whether in the stagnant lid or below, it can be mixed in the interior or not. Yeah, so it really strongly depends on the parameter of the viscosity. And this now has been tested in a model here. It's kind of a busy slide, but let me explain you what we see here. So here is a radius, and here are different viscosity profiles for different mantle material. This is a very low viscosity, assuming that you still have melt in the interior or a lot of water, so low viscosity, and here the viscosity is increasing. And these are different models for different activation energies. So what we see here is the fraction of overturned IBC as a function of time. So when you end up to 100%, that means that all the IBC sink down into the interior. And what you see here is, or what you can't see because we haven't plotted it here, but for a high viscosity higher than 10 to the power of 21, which is would be similar to a stiff and dry mantle, all the IBC layer, because there is no line indicated here, but for all these models, the IBC would stick in that layer here, below the surface. Yeah, but for lower viscosities, it is possible that you see here for the red case where we have a reference viscosity of 10 to the power of 20, part of the IBC can sink into the interior, and for very low viscosity, basically everything sinks into the interior. Here are two different cases where, in that case, the IBC layer has the same rheology than the mantle material. In that case, we have assumed that the IBC layer has even a lower viscosity. In that case, the efficiency of bringing the material into the interior is more efficient. So to conclude that so the sinking is more efficient the lower the viscosity of the mantle and the IBC layer is, and also the lower the activation energy. This is also now a lot of detail, which is probably not important here, but I think what you have to remember is a low viscosity in the mantle would basically allow that the IBC layer is sinking down. And the next point is now how much, in what way does this IBC layer sinks? And what we see in these models is that they basically sink as small diapirs, what you see here. So that is a composition, that is a temperature field at different times. So here's an initial stage where almost nothing had happened. You see some small drips here, and with time these drips are increasing. You have a lot of drips, and it is sinking in the interior. And here you have a lot of IBC basically mixed in the mantle. And that is the next point here. So part of the IBC is accumulated at the core mantle boundary, and part of it is mixed in the mantle. So we have stopped here after 10 million years. You could basically calculate longer, but you end in a similar situation that you have part of the IBC layer at the core mantle boundary, and part of it is in the mantle. And actually, depending on the viscosity, which we don't know exactly what it is, would also stick below the crust. So you have a situation where you can have different configuration where the IBC layer is located. Okay, another thing is now that there's also a lot of literature arguing that the Pikati region is formed by a low degree downwelling. For that, you have to know that such a low degree downwelling can only be possible when this IBC layer is thick. Thick means 150 kilometer or even thicker, and should have a very low viscosity. And that what you can see here is kind of a Rayleigh-Taylor instability study, where when you see here the yellow line here illustrates where you have the peak is the degree which is initiating the fastest. So where you have the peak, the yellow is the degree 1, and for that you need a thick layer for the same viscosity ratio. So 10 to 4 means the viscosity of the IBC layer is a factor of 10 to 4 smaller than the viscosity of the mantle. So with decreasing IBC layer, you see that the higher degrees become unstable. So that doesn't work, so need in the thick. And here is the ratio of the viscosity varied. So this is a ratio of 10 to 4, as I just said. So the viscosity of the IBC needs to be very small. If it is higher, the viscosity, we have the same situation that you have a higher degree, which becomes unstable. So that's what we don't want to have. So what we need to have is a thick layer with a very low viscosity of the IBC. And if you remember what I said, when you have the normal crystallization, the IBC layer is thin with a thickness of 20 to 40. So that would not work. So it has been suggested now that you basically can form such a thick ilmenite layer by consider that when you freeze out the magma ocean, it takes quite a while. I mean, it takes something like 200 million years. So the point now, the idea is now that during the solidification, you form a diluted but still dense layer, which had a large thickness, and which then becomes unstable and forms this low degree downwelling. The question now is that scenario realistic or not? Because from the situation before, we've seen with a thin layer, it is not possible, and you need a thick enough IBC layer with an extremely low viscosity. And it has been realized now by experiments that the ilmenite has a low viscosity, so that is a possibility, although it is not that low. But if you consider there's also melt in this layer, there is a possibility. But still, is the situation realistic to form this so-called MIC layer? And for that, I show you that slide here. So the idea then is when you start crystallizing, you first have a thin IBC layer, which is then growing in thickness, but it is a slow process. So what you can do is you can basically calculate the Stokes velocity of smaller dips, smaller diapirs sinking down before the whole layer becomes unstable. And doing that, so you see here the equation of the Stokes velocity, you can calculate the size of the diapirs here that will be formed. That is a time scale of instability of this layer, and this is how to calculate the wavelengths, basically from that the size of the diapirs. So I mean, you can look at these equations later with more in more detail, but if you plug in all the numbers of the viscosities and so on, you see, or give you one example. So assume that you have a mantle viscosity of a power 10 to 19. So you basically can calculate for a 20 kilometer thick IBC layer at the end, yeah, which solidifies in 200 million years. So with a rate of 0.1 kilometer per million years, then in that case you form a 2 kilometer diapir and that sink a maximum of 80 kilometer. So in principle you could generate for this specific scenario an 80 kilometer thick IBC layer, which is diluted but still sufficiently dense to have then a low degree downwelling. But now comes the problem. So if the viscosity is low enough for those small diapirs to sink, convection of the whole thing would start already earlier. So you bring directly these diapirs down into the convecting mantle. The other situation is if the viscosity is high, that you don't have convection in the cumulate mantle. The problem is that the diapir will not sink. They will sink much too slow. So there will be no formation of this so-called MIC layer. So the conclusion is that a low degree downwelling is highly unlikely because you never have the situation to form this layer unless it is mixed due to convection of the cumulate layer directly. So there is no way of getting a low degree downwelling. At this point, I want to also mention there was the idea that we can have low degree upwelling. That's a different situation. So we have already the IBC at the core mantle boundary. And this IBC layer, it has a high density, but it also brings a lot of heat sources with it. And you can heat up this dense layer from the core mantle boundary and it becomes unstable. And under specific situation, it can have a low degree upwelling in case of a temperature-dependent viscosity, a weak temperature-dependent viscosity. It has been shown now, actually with the same authors now, that this is also very unlikely because, as I said, the IBC has a low viscosity. It has been shown from experiments. So when you consider that, you end up again with not with a low degree upwelling, but with upwelling with a lot of plumes, basically. And this is also a situation which is not consistent, you can't use to explain the Pikati. So the conclusion here is actually that for to explain the Pikati region, there is neither with low degree upwelling nor with low degree downwelling is a possibility. So we need to have other mechanisms for that. And one possibility has been suggested that it is formed by an impact, for instance. Okay, a few words about the long-term evolution. I've mentioned already that we have this so-called stagnate convection, where we form a stagnant lid on top, which is different to what we know from Earth, where we have plate tectonics. And the cooling of the interior looks different. So what you see here is a function of radius and time. The temperature distribution, you nicely can see here that the lid is growing, so you cool from above, but the interior basically remains at the same temperature. Yeah, so the cooling in the interior is not very efficient, but you cool from the top. So now the big point is, I mean, we observed we have long-standing volcanic activity on the moon. And people thought, oh, it's very difficult to get because we have a small bunny, which typically is cooling fast. But the magic here is again the crust, because the crust has a very low conductivity. In particular, you have this regulus and mega regulus where you break the crust, which suggests also a further reduction of the thermal conductivity. And you nicely can see here for two different models where we assumed a lower thermal conductivity of the crust, that you can have a volcanic or partial melt in the interior up to the present day, depending on the thermal conductivity of the crust. So that is actually no problem, yeah, to have a long-standing volcanic activity on the moon. Okay, and the last I want to show is the influence of the Pikati region on the thermal evolution. So in that model, it was assumed that we have, so it assumes that the heat sources are already enriched in that region, and looks what is then the influence on the dynamics. Yeah, so it doesn't provide you an explanation how that Pikati region is formed, but gives you an idea what is the influence of such a region, and that you can see here. So what you see here are temperature slices at different times, 4 billion years ago up to present day. This white area here is where partial melt is generated. So that is the region where the Pikati region is located, and that is antipodal. So what you see here is that it's actually a qualitatively match of the duration of the lunar volcanism. Again, that is the effect of the insulating effect of the crust. We see an asymmetry in the near and far side in the magma production. So that would be the near side and that would be the far side then. We have the location of the youngest eruptions in the Pikati region. And what you see here is the surface heat flow as a function from the center of the Pikati region. You probably know we have heat flow measurements from the Apollo 15 and 17 landing sites, which is also consistent to this kind of model, which suggests the influence of the heat sources on the mantle dynamics seems to be very strong and would also suggest that today the surface below the Pikati region is higher than antipodal to that in other regions of the moon. Okay, I think I'm already late. So here you have some take-home messages about the Magma Ocean, which sets the stage of the planet. So we have fractal crystallization, the anorthositic crust, and accumulated mantle. The solidification time is longer than people have suggested. So it's more like 200 million years due to the crust and the volcanic heat transfer. We have mixing of the ilmenite into the mantle and partially sinking at the core metal boundary. Ilmenite will likely sink as small diapirs. There is no formation of a thick ilmenite layer or something like this. Therefore, also no degree, low degree downwelling, and which I haven't addressed, but the ilmenite close to the CMV layer may be partially molten because it has a low melting temperature. And this has been also indicated from seismic data, actually, that there could be some partial melt at the core metal boundary. So for the Pikati region, the origin is unclear. There's a possibility of an impact which have caused this region. So the old ideas, low degree overturn or upwelling, both do not work. But there's a strong influence of this enriched layer on the mantle dynamics and convection pattern, also for the volcanic activity, which could also explain why we don't have at the SPA basin, that we don't see strong volcanic activity there. And concerning the duration of the Mara volcanism, that's easy to understand if you consider that the anorthositic crust is isolating because of its low thermal conductivity. And this I haven't addressed, but what we typically see that there's when you have the impact basin and there's typically a delay of 100 million years, that could be the reason due to upwelling mantle material. When you have an impact, it takes some time for the mantle flow to get up and to melt there. That could explain the delay of magnetism. So, and with that, I conclude, and I have 2 slides of literature, which I've used in the presentation. But I'm happy now to take questions. Thank you.